Okay, welcome to page 103. We are going to look at example 2 together. Okay, and example 2 gives us two linear operators on R3 and just asks us to determine whether or not they're diagonalizable. Now, before we dive into this, let's remember how we can do that. Okay, diagonalizability has to do with being able to find a basis that consists of eigenvectors. So our vector space in this case is R cubed. And so if we want a linear operator to be diagonalizable, that means we need to find a basis for R3 that consists of eigenvectors of that. Okay? So for each of these two exercises that we do, we're going to have to start by finding eigenvectors. And let's start with the first one here. We're talking about a linear operator T1, and just to shorten the process, some of the calculations have been done for us. Okay, so they're giving us the matrix for this linear operator, and they also gave us the characteristic polynomial. Okay, now notice we're using t's instead of lambdas, but this is the same calculation that you would do if you were going to find eigenvalues. Okay, you'd take the determinant of a minus lambda I, you'd do all of the algebra, and you'd come up with this polynomial and set it equal to 0. Okay, and you can see that the two solutions to that equation, if you set that equal to 0, are 4 and 1. Okay, and that's why we're getting these two eigenvalues down here. Okay, and they've even taken the calculations one more step by actually forming the matrix A minus lambda I. Okay, that's what you would get if you subtracted 1 from all of the three main diagonal elements. Okay, we'd set that equal to 0 and do row operations, and here's our reduced matrix. Okay, and notice we've just got one pivot position. Okay, so that means we actually have two free variables in this case. So if we want to solve that system, maybe let x2 be t and x3 be u. Okay, and I'm trusting you could do the algebra and solve for x1, and if you do, what you're going to get is 1/2 t plus 1/2 u. Okay, and then we'd go from that and try to find a basis for the eigenspace associated with lambda 1. Okay, and we know that because we've got two free variables, we need two eigenvectors to get the basis. So if you think back to the process, okay, it consisted of kind of taking our free variables one at a time and setting them equal to something that's non-zero. So we might start by letting t be 2 and u be 0. Why did we choose 2? Well, it's kind of a way of getting rid of that 1/2 that you see. Okay, so if you make those two choices for your free variables, substitute into x1, x2, and x3, you're going to get an eigenvector that looks like 1, 2, 0. You can confirm my calculations there. Okay, and then to get the second eigenvector, we could just make a different choice. This time we'll make t equal to 0 and u equal to 2. Okay, and if you go back and substitute those into these three equations, this time you're going to get 1, 0, 2. Okay, and those two eigenvectors together should span our first eigenspace. All right, so we can go up, and they asked us for a basis for E lambda 1. We've just found it, or one possible one anyway. Okay, and then we move down, do a similar calculation for the second eigenvalue, 4. Okay, again, they've taken care of the first part of the calculation for us, formed the matrix A minus lambda I and reduced it for us. This time, we have two pivot positions, so there's only going to be one free variable. Okay, x3 equals t. And I'll leave it to you to confirm that with that choice for x3, x2 and x1 are going to look like 0 and t. Okay, and this time, we just have one free variable. Okay, so E lambda 2 should be spanned by just one eigenvector. Okay, so if we let t be 1, we're just going to get 1, 0, 1. That should be enough to form a basis for E lambda 2. Okay, so what about diagonalizability then? Is T1 diagonalizable? Okay, well again, that comes down to the question of, is there a basis for R3, our vector space that consists just of eigenvectors? There actually is, because of the fact that if we put those three eigenvectors into one set, we actually get a basis, okay, for R3. All right, so let's put that into words here. T is diagonalizable. Okay, because beta equals, we'll just make a set with all three of these eigenvectors in it. Okay, and I'm going to use a strange word here, appears to be a basis for R3 consisting of eigenvectors. Why do I say appears? Well, we didn't check to confirm that beta really is a basis. We would have to do a calculation and confirm that those vectors are linearly independent. I'm trusting, though, that you could do that, and that would confirm that we do have a basis of eigenvectors, and by theorem 5.1, that means that this is diagonalizable. Okay, and that concludes our solution for T1. Okay, and for T2, I'd like you to actually pause the video here and see if you can do T2 on your own. Okay, it's going to be the same process. You're going to find your eigenvectors and ask the question, is T diagonalizable based on that? Okay, so take a minute to try that. Welcome back. Okay, so hopefully you've tried the second part of this exercise. Let's run through that together just so that you can check your answers here. Okay, same starting point as before. This time we've got a new linear transformation T2, and they've given us its matrix. They've gone ahead and calculated the characteristic polynomial. Okay, and we can look at that and see what our two eigenvalues are by setting that equal to 0. We're going to get the same two numbers that we did before, 1 and 4. Okay, our matrix is going to look a little bit different in this case, but they've done the row reduction, so let's start with lambda 1 equals 1. We reduce down to this matrix. Where's our pivot positions? Okay, well, I only see 1 in this case, right there, which means that x1 and... Oh, actually, I apologize. There's actually 2 pivot positions, aren't there? Okay, because pivot positions are the first non-zero entry in every row. So there's another pivot position. Okay, so we've actually got only one free variable in this case, and it's x1. Okay, and you can maybe see from that system that if we take those two equations and solve for x2 and x3, we're going to get 0 for both of those. Okay, so we've only got one free variable, which means that we should be able to span our eigenspace just using one vector, and a natural choice for our free variable is just to let it be 1. So if t is 1, notation, E lambda 1 is going to be the span of that one vector. All right, so we have a basis for the first eigenspace. All right, we do the same calculation down here for lambda 2. Okay, this time, let's see, we've got pivot positions here and here. Okay, so x3 is a free variable. Okay, and if you go ahead and solve for x2 and x1, okay, you can confirm my calculations here. You're going to get 0 for x2 and t for x1. Okay, so E lambda 2, our eigenspace, can be spanned again by just one vector because we've got one free variable. And if we let t be 1, we're just going to get 1, 0, 1 this time. Okay, so a basis for E lambda 2 is 1, 0, 1. Okay, there are our eigenspaces. Okay, and so now comes the question, is T2 diagonalizable? Okay, well again, this comes down to answering the question, can we find a basis for R3 that consists of eigenvectors for this linear transformation? Well, how many eigenvectors do we have? This time there are only 2, and 2 vectors is not enough to form a basis for R3. Therefore, the answer has to be no in this case. Okay, so let's write that down. Okay, so it's not diagonalizable because there are just not enough eigenvectors in this case. Okay, so hopefully that's the answer or the conclusion that you came to.